You'll recall from English class that a sentence that contains the word and or is known as a compound sentence. Well, in math, algebraic sentences can also contain the word and or, and they are also known as compound sentences. So two familiar situations in which this occurs is when we are considering the intersection of two sets. Now, the intersection, given by this upside down U symbol here, simply are all the elements that are common in both sets. So think of the elements of set A and the elements of set B, and their overlap are the ones that are in A and B. And that's known as the intersection, and that represents the word and. The other word that we're looking at here is the word or, and it represents the union of two sets, and it is all the elements in one set or the other set. So literally it consists of all the elements. So let's take a look at these two examples. Here we see we want the set of all x's that are greater than 4 and less than or equal to 8. So if I place 4 here on my number line, 5, 6, 7, and 8, I want everything that is greater than 4, and I want everything that is less than or equal to 8. So when I combine these two and put them together, I'm going to have an open circle here at 4, extending to the right until I get to 8, and then a closed circle. Now, you'll also recall from earlier math classes that anytime we want something greater than or less than, we are going to have an open circle. And anytime we have something that's less than or equal to, or greater than or equal to, we're going to have a closed circle, indicating that it can be equal to that value. Let's take a look at the union then. Here's an example. We want all x's that are less than or equal to -3. So we'll place -3 on our line here. And it's going to get an open circle and an arrow extending off to the left. Or we want all the elements that are greater than or equal to 5. So here's -2, -1, 0, 1, 2, 3, 4, and 5. We'll place 5 on our number line. And this will get a closed circle with everything extending out here to the right. Let's take a look at a few more examples. Example A, we see that we have this intersection sign, so this is the overlap of these two sets. We want all the x's that are greater than 8, so open circle here at 8 and everything extending out here to the right. And we want everything that is greater than or equal to 4, so a closed circle here at 4 extending out here to the right. Now, since this is an and, we want the overlap of those two sets, so what's in both sets? So what's consistently in both sets is everything that's at 8 and greater than. So we will color that in here on our number line, indicating that this is the solution to this intersection set. Our next one is also an and, so again we want the overlap. We want all x's that are less than or equal to 8. So I'll put a closed circle here at 8 and extending to the left. And everything that is less than 4. So I'm going to put an open circle here at 4, extending everything here to the left as well. Now the intersection of these two sets here is where it's opened at 4 and going to the left of 4. So my solution here is the one on the number line, open circle at 4, extending to the left. Next, let's consider the union of these two sets. So this is the case of or, so we will actually graph all elements here. X's were greater than or equal to 8, so we'll put a closed circle here at 8 and extending to the right, indicating all the values greater than or equal to 8, and less than or equal to 4. So again, a closed circle here, extending to the left, and this is our solution. Both of these branches represent the union of those two sets. All right, moving on to example D now, we see that we have x less than or equal to, less than 8, and we want the intersection of that, and x is greater than 4. So we have an open circle at 4 extending off to the right. Well, if I want the overlap of these two sets, I see that I have to have an open circle at 4, an open circle at 8, and everything in between 4 and 8 on that solution set. The next one is the union of these two sets, so where x is less than 8, so open circle here at 8, extending to the left, and greater than 4, so open circle here at 4, extending to the right. Now, since this is a union, or it's the case of the or, then it's actually all real numbers because it's in one set of the both, and since we have a line that extends in both directions forever and ever, then this is going to be a set of all real numbers as our solution. All right, finally for f here, we see that we are back to the intersection or the overlap. This represents the word and. So we want all the values greater than 8 and less than 4. Well, since we're looking for the overlap here, and neither one of these two branches overlap, this is actually known as the empty set, or we could say that this is no solution. All right, now let's go back the other way, looking at the branches of the graphs that we're given and see if we can write the double inequality. Well, it looks here that we have not an overlap, but more of a union of two sets. So it looks like we have the union of set where all x is less than -1. It's not equal to -1 because you can see here that there's an open circle at -1. Or all the x's that are greater than or equal to +5. And again, it's equal to because we have a closed circle here at +5. Now, if we wanted to write this using our symbol, we could say that it's x less than -1. And the symbol for or is the union, x greater than or equal to 5. In our next example, we see that we do have an overlap of two sets, and so we are going to be using the and, or the intersection. And we see that we have all x's that are greater than or equal to -2 and all x's that are less than or equal to 4. So another way to express that is we could say x greater than or equal to -2. The and is the upside down u, and x less than or equal to 4. All right, now taking a look at a few equations, inequalities, solving for these inequalities, our addition property of inequality and our multiplication property of inequality exist in similar fashion to the way that they do for addition property of equality and multiplication property of equality, except for one instance. Only when we are multiplying or dividing by a negative number, we have to keep in mind that we need to switch the direction of our inequality. So in solving this inequality, we are going to start by adding the 4 over. So we have 35 on the right-hand side, and now we're going to divide by -5. And here's the instance of when we divide by a negative, we must switch the direction of the inequality. 35 divided by -5 is -7. So my solution is all x is greater than -7. So if I put -7 on my number line here, I'm going to have an open circle, and everything to the right indicating all values greater than -7 will make this a true statement. Two more examples now. Let's take a look at solving these equations and inequalities. Whenever we are taking the square root, we have to allow for both the positive and negative solution to occur. So this is an example of solving a problem and it being a compound sentence of and. So when I take the square root of x, I get x. When I take the square root of x squared, I get x. And when I take the square root of 4, I get both a +2 and a -2. So the solution here is both my -2 and my +2. Likewise, over here on the right-hand side, I'm going to start by dividing both sides by this -1. And again, I need to apply my multiplication property of inequality. That states that I'm now going to be left with x squared plus 3 is less than or equal to +12. Subtract my 3 over, and now I have 9. And now I'm going to take the square root of both sides. So when I do that, I have x is less than or equal to +3, and x is greater than or equal to -3. So when I take that square root in an inequality situation, I'm going to solve for the positive value. That will keep the sign pointing the same direction. But then I must also consider the negative value, and that will change the direction of the inequality. So now I have all values greater than or equal to -3, but less than or equal to +3.